So today we're going to discuss one of the important phenomenon in when we talk about mechanical behavior of materials. So we will talk about the creep from the perspective of material science and its importance in mechanical behavior of materials. So what does it means by creep? So we can say that a creep is a kind of a specific plastic deformation. It is a time-dependent deformation under a certain applied loading, and it generally occurs at a high temperature, or we can say as a thermal creep. But it can also happen at the room temperature in certain materials, for example, such as lead or glass, although at a much slower rate. And as a result, the material will undergo a time-dependent increase in length, which could be dangerous while in service. Creeps will terminate in rupture if steps are not taken to bring it to halt or stop it. Diffusion, dislocation glide or climb. Diffusion, dislocation glide. Or climb. Or grain boundary sliding, grain. All these can contribute to the creep of metallic materials. So the rate of deformation is what we call as a creep rate. Creep rate. It is the slope of the line in a creep strain versus time curve as what we have here in the figure. So the results of creep test is usually plotted as a creep curve where we plot a strain. We plot the creep strain as a function of time because we are keeping the stress constant. So unlike what we have in a strain diagram, in the case of a creep, we have a strain time diagram because it is a continuous plastic deformation as a function of time. So we can say that a strain is plotted as a function of time. The minimum creep rate change in strain over time is the slope of the linear segment in the secondary region here. And the rupture lifetime, T not R, is the total time to rupture. So here is some characteristic of a creep. A creep is a time-dependent permanent plastic deformation, which generally occurs at a high temperature at T higher than 0.4 atm or melting point under a constant loading or stress. It can also happen at the room temperature for a soft metal such as lead, like what I have mentioned before, glass. It is a very slow process where deformation changes with time. Creep is important in applications such as a turbine blade, in a jet engine, gas turbine, power plants, such as a boiler and a steam line, which must operate at the high stresses and high temperature without any changes in dimension. So here is some creep, characteristic of creep. Creep in surface is usually affected by a changing condition of loading and temperature. And the number of possible stress temperature time combination is infinite. And the creep mechanism is often different between different types of materials such as metal, plastic, rubber, or concrete. Creep is a time-dependent deformation under an applied load. Metals or alloys do not exhibit a time-dependent deformation under a normal surface condition. So when a metal is subjected to a constant loading at elevated temperature, the metals will undergo a time-dependent increase in length. So we have a strain versus a time graph. This diagram this figure shows a strain as a function of time. Strain as a function of time, like what I have shown you in previously. The portion are split as a primary, secondary here, and tertiary curve. In the beginning, here, the rate of strain is quite high, and then it stabilizes due to the work hardening. And then we have in the second segment, the strain is minimum and nearly constant, which happens as a result of a balance between annealing and work hardening. Annealing and work hardening. And then we have a tertiary segment that is similar to the necking phenomenon observed when metals tension tested in a universal testing machine. So the strain versus time graph are plotted with a constant loading applied at a constant temperature. The shape and the creep curve will depend on the levels of the temperature and the stress that we apply. And if the temperature is remain constant, if the temperature is remain constant, then the creep curve will shift upward and to the left with increasing applied stress. We will talk more about that later. So here we also have a creep rate versus time graph. And here we can see that in a primary creep stage, the creep rate decrease until it reaches a steady state creep that will occur for a very long time. Yeah. And this period of almost constant creep rate, at this stage is the period that forms the bulk of the creep life of a component until it reaches a tertiary creep stage when the creep rate suddenly increase until the materials reaches a failure. So here we have the third stage, what we call as a tertiary creep, occurs when the creep life is almost exhausted. Voids have formed in the material, like what we have learned in a previous lecture when we apply force or stress to a specimen. Voids will form in the material, especially when we apply the force in a tension manner. And the effective cross-sectional area has been reduced. And here, what we will have is the creep rate will accelerate, and as the stress per unit area increase until the specimen finally fail. And this typical failed specimen is illustrated in a figure here. So here we have an example of a typical failure specimen when we apply that experience creep. So here we have some of the definition of a creep stages. We have a primary creep where the slope or creep rate decrease with time, strain hardening occurs, and then we have a secondary creep where that can be described as a steady state. The rate is constant and the plot becomes linear, and then we have a tertiary creep where there is an acceleration of rate and ultimate failure. So the deformation process in creep, which occur at the elevated temperature, are due to the dislocation or movement known as slip dislocation or slip, or it can be due to the grain boundary sliding, grain boundary sliding, or a sub-grain formation. So all these, the deformation process in creep that occur at the elevated temperature are due to all these phenomena. And at the increasing temperature, slip systems are more available. I hope all of you still remember what is the definition of a slip system that we learned in chapter 3, if I'm not mistaken. Grain boundary sliding is a type of shear process along the grain boundaries that provide a non-uniform amount of shear displacement. The deformation of a subgrain, normally in the adjacent of the grain boundaries, will result from the lattice distortion, and this allows a dislocation with opposite signs to form in the subgrain. And here we have another characteristic of each creep stages. In primary creep, in the primary stage, a creep starts at a rapid rate and slows with time. In secondary stage, a creep has a relatively uniform rate, and in tertiary stage, the creep has an accelerated creep rate and terminates when the material breaks or rupture. So now we will be discussing the stress and temperature effect on a creep rate, and there are various types of a creep deformation, like what I have mentioned before, including dislocation creep, diffusion creep, or bulk diffusion or grain boundary diffusion, dislocation climb, glide creep, and thermally activated glide creep. And all these different creep mechanism will depend on the temperature at which a deformation is happening, and the stress level experienced by the material, and also the material's microstructure and composition. And the effect of a temperature and stress can be observed in the figure here. So here we have at the temperature below the 0.4 or 40% of the melting temperature, and after the initial deformation, the strain is visually independent of time. But with the increasing stress or temperature, the instantaneous strain at the time of stress application increase, and we can see that the steady state creep rate is increased, and the rupture lifetime is decreased. So what we can conclude here is we can say that creep is temperature dependent. Creep is temperature dependent. When our specimens is hotter, the more creep strength will be, and the faster creep will occur, especially for metals, where the creep really took off at 40% of the melting temperature. So here we have the effect of stress and temperature on a steady state creep. At a constant temperature, the steady state creep data will follow this equation. Here we have, maybe you cannot see it clearly, here we have a change in strain over time equals to C, sigma, and N, where C and N are material constant. In some reference, we can replace C with K. When stress is constant, steady state creep will follow this equation. Here we have a D equals to A, give Q and RT, where A is a constant, Q is the activation energy, R is the gas constant, and T is the absolute temperature. So here we have a creep test. A creep test involves a tensile specimen under constant loading maintained at a constant temperature. And the measurement of a strain are then recorded over a period of time. So as what we already know, creep is a high temperature progressive deformation at a constant stress. So when we say a high temperature, it is a relative term that dependent upon the materials involved. Creep rates are used when we want to evaluate materials for application such as a boiler, a gas, a turbine, jet engine, oven, or any application that involve a high temperature underloading. So understanding the high temperature behavior metals is very important when we want to design a failure resistant system. So if we want to determine the creep characteristic of a material, a constant stress is applied to a heated specimen in the creep testing. And as soon as the stress is applied, the specimen will stretches elastically to a small amount, strain knot, like what we can see here. And depending on the applied stress and the modulus of elasticity of the material at a high temperature, creep testing can also be conducted under constant load, and it is quite important from an engineering design viewpoint. So during the creep testing, the strain or elongation is measured as a function of time and plotted to give the creep curve, like what we have discussed previously. And in the first stage of a creep of the metals, so I give metals as examples of materials. So in the first stage of a creep of metals, many dislocation climb away from the obstacles, like what we can see in the figure here, and contribute to deformation. And eventually, the rate at which dislocation climb away from the obstacles will equal to the rate at which dislocation are blocked by other imperfection. And this will lead to the second stage or steady state creep. and the slope of the steady state portion of the creep curve is the creep rate, like what we can see in the equation here. So the creep rate and rupture, T not R, T R, will follow an Arrhenius relationship. Arrhenius relationship. That consider for the combined influence of the applied stress and temperature, like what we can see in the equation here. So here R equals to the gas constant. R is gas constant. T is the temperature. Temperature in Kelvin. And C, we have a C, K, and M are all constant for the material. M are all constant for the material. QC is the activation energy for creep. Activation. Creep. And QR here is the activation energy for rupture. So in particular, QC is related to the activation energy for a self-diffusion when dislocation climb is important. So in a crystalline ceramic, other factors including a grain boundary, sliding, and nucleation of a microcrack are particularly important. Oftentimes, non-crystalline or glassy materials is present at the grain boundaries, and the activation energy required for the glass to deform is low, and this will lead to the high creep rates compared with a completely crystalline ceramic. And for some reason, the creep that occurs at the rapid rate in ceramic glasses and for the same reason, the creep occurs at a rapid rate in ceramic glass and amorphous polymer.